Good morning, everybody. Right now, we are going to review the last concept that we talked about in class yesterday. So we ended our chapter 10 discussion talking about the Bronsted-Lowry definition for acids and bases. The Bronsted-Lowry definitions for acid and bases establishes that an acid is going to be a molecule that is going to donate a proton. And remember that a proton is an H+. Then the base is going to be the molecule that accepts that proton, okay? Now, we learned yesterday, as you can see in part B and part C, that we can actually write the chemical formula and the formal charge for the molecules that are conjugate acids or conjugate bases for Bronsted-Lowry acids or bases, okay? So as you can see in part B, we were writing the conjugate base of a Bronsted-Lowry acid. And remember that if something is behaving as an acid, overall, we are losing an H+, and we have the rules right here in the corner for how the formal charge changes. On part C, we were actually writing the chemical formulas for the conjugate acid, given that the molecules on the list are Bronsted-Lowry bases. And whenever we're writing the conjugate acid of a Bronsted-Lowry base, we are adding one H+ to our chemical formula. At the end of class, we were going through, if you are given an acid-base reaction, then understand that you need to identify what is the acid, what is the base, what is the conjugate acid, and what is the conjugate base. So when it comes to the last example that we have, as you can see here, we have ammonia and we have sulfuric acid forming HSO4- and NH4+. So if we label these molecules, we can see that ammonia changed to NH4+. That means that we added a proton to it, okay? So what is the role of ammonia in this reaction? Is it an acid or is it a base? Let's put it in the chat. Is ammonia an acid or a base? Excellent work. This is a base, because remember that that base trapped an acid from somewhere. And who is the acid? Well, sulfuric acid. Now, because ammonium came from our base, is ammonium the conjugate acid or the conjugate base in this acid-base reaction? Excellent job. This is the conjugate acid. So when this acid loses, so minus H+, when it loses a proton, then it creates a conjugate base. Any questions about Bronsted-Lowry conjugate acids and base pairs? Then let's move on to the next concept, which is section 10.3. Now we are going to learn about acid-bases equilibrium. So understand that the concept of equilibrium in a chemical reaction is when no further changes in the concentrations of the reactants and products are occurring, okay? So what that means is that if we have a reaction that is going from reactant to products, and those products go back to reactants, okay, we have a rate of the reaction in either the forward direction, and the forward direction is given by the forward arrow. So this forward reaction is given by the forward arrow. And then we have a reverse reaction, which is given by the reverse arrow, okay? Now, we can see in an illustration on the right side of the slide that this is how we can map a reaction that is in equilibrium. As you can see, as the reaction's time progresses and we look at the concentration, our reactants is going to decrease. And it makes sense because the reactants are turning to products. The products curve, which is the blue line, is going to increase. And when we don't have changes in the concentrations of them, that's when we say that the reaction is in equilibrium. Now, this whole idea of equilibrium is actually ruled by the following principle, which is called the Le Chatelier's principle, okay? And in Le Chatelier's principle, it is defined as when the equilibrium of a particular system is disturbed, then the system is going to change the rate of either the forward or reverse reactions to relieve that stress and reestablish that equilibrium. Now, understand that you may be like, why would reactions go forward and backwards? In class today, we are going to learn how specifically there are reactions in our bodies that have to actually occur in order to reestablish the equilibrium of the system. And it's going to be related to pH. If you have taken physiology, maybe you have heard of those concepts before, but we will explain them towards the end of today's class. So understand that this whole system of equilibrium, it can happen in even normal chemical reactions, and we need to pay attention to them, okay? So understand that we can utilize the analogy of a water tank to really understand the Le Chatelier's principle. And if we focus on the middle of this slide, we can see that here we have a water tank that has two compartments. And at first, you can see that our system and our water inside that tank with the two compartments is at equilibrium. Let's say that, for example, to disturb this equilibrium, we are going to add more water to the compartment A inside of this tank. Well, in order for the system to equilibrate again, then understand that you need to increase the rate of the forward direction, meaning that the water is going to rush towards the next compartment in order for the system to be in equilibrium again, okay? Specifically. Now, there are many things that can affect the equilibrium of a system, okay? Now, understand that in this class, in Chemistry 104, we are only concerned with two things in our chemical reaction, okay? Which is going to be concentration of reactants and concentration of products. That's the only thing that we're going to study. Understand that in equilibrium reactions, temperature affects it, pressure affects it, even the state of matter of the components of your chemical reaction affects it. But again, in this class, we are going to simplify the concept and we will only be concerned with concentration of reactants and products, okay? So as you can see, when we alter the concentration of reactants and products, understand that similarly to our water tank analogy, the rates of the forward and reverse reactions will no longer be equal, and then the rates needs to be adjusted in order to regain equilibrium. So how are we going to deal with this? Then you need, for exam 2, to understand how to utilize table 10.4. So we need table 10.4 in the exam. In table 10.4, understand that we have the different types of stresses that we're learning in this class, which is addition of reactant or removal of reactant, addition of product or removal of products, okay? Understand that the second column in this table tells you what's going to happen to the rate of the reaction. So that change is going to be what happens to the rate of the reaction. As you can see, if you add reactant, the forward rate of the reaction is going to increase. If you remove reactant, then that decreases, okay, the reaction rate of the forward direction. But that means that it increases the one in the reverse direction. It's just that this is going to give you, in terms of the rate of the reaction, only half of the story. When we are adding product, we are going to increase the rate of the reverse reaction. When we remove products, okay, this means that we are going to decrease, okay, the reverse reaction. Understand that the third column, which is the shift of the direction, will be like, since we are moving the rate, okay, wait, let me just rephrase that because that didn't sound correctly. So when we are talking about the shift in the direction, will be like which rate, okay, is going to be the most affected? Is it going to be the one that is pointing towards products or reactants? So that's what we see in that third column. In order to better understand this process, let's do some examples, okay? And give me a moment. Let me just bring the water tank. Let me just bring this one.
Professor, I have a question.
Yes, go ahead.
So really, is it just because it's moving from high concentration to lower concentration, and then that triggers like the forward and reverse reaction?
In a way, yes. We are increasing concentration because we're literally like taking the vessel and adding more reactant, okay? Or we're taking the vessel and we're removing more reactant. So you are changing the concentration, that, or it could be product too. So that's what creates the shift, that we are increasing concentration or decreasing concentration of either reactants or products. Let's actually go over an example. There you go. Let me just put it here. Oh, let me just put it below. So I'm going to label, let me just move table 10.4 a little bit more up. moving everything. Okay. Let me see if I can make this larger. Give me a moment. Let me redo this. Okay. Let's look at reactions that are in equilibrium, and let's determine what happens overall to the system. We are going to utilize the water tank analogy along with table 10.4. So you guys know how to deal with these questions when it comes to the exam. So we can see in the corner that we have the following reaction that is in equilibrium, okay? We have SO3 decomposing to make SO2 and O2, okay? So that is our system in equilibrium. When it comes to table 10.4, I'm going to use letters to identify each of the different stresses that we're going to do to the system, okay? So in problem 1, the first statement says sulfur dioxide is added to the system, okay? So if I use my water tank, that means that my reactants are going to be in one side of my tank. In this case, it's going to be SO3. And then my products are going to be on the other side of the tank. This is where we have SO2 plus O2. For my students that need to take further chemistry classes, understand that equilibrium systems must have, or the molecules in the system that are affected by stresses in equilibrium must be in aqueous form or gas form. Anything that is in a solid form or liquid form, understand that even if you make changes to them, do not affect the equilibrium, because in chemistry, we consider that things that are in solid or liquid form have a constant composition. So only molecules that are found in gas form or aqueous form are the ones that are going to affect the equilibrium of a system if there's changes done to them. So in this system, on statement A, it says sulfur dioxide is added to the system. So if you're utilizing table 10.4, does that statement refers to A, B, C, or D? Let's put it in the chat. Sulfur dioxide is added to the system. Excellent. Thank you for putting the letter C. So this, let me use a color coding. So this is letter C. If I use my water tank analogy, this means that I open this container, okay? And all of a sudden, what is happening is that we are adding water to this side, okay? If we look at what happens when you add products, it increases the reverse reaction. And in a way that makes sense, because if you increase the level of the water here, it's going to rush towards the first tank, okay? So we are increasing the reverse reaction. And as you can see, the shift of the direction of the reaction is going to be towards reactants. Put a 1 in the chat if letter 1A makes sense based on the information on 10.4 and the information on the analogy of the water tank. Let's move on to the second one. In letter 1B, it says sulfur trioxide is removed from the system. So does that refers to A, B, C, or D? Excellent job. We are removing reactant. So let me just and make changes here, because when I erase, it erased everything. Let me see if I can erase smaller portions. So when it comes to this, let me write the balance equation, because that will be more appropriate. So in statement B, it's kind of like we are opening the vessel and we're letting water rush from the system. So when that is happening, since we are lowering this level, then you can see that letter B says it decreases the forward rate. Makes sense, because we're not going to have water rushing from A to B. It's going to be going backwards. And the shift of the direction, if this level is decreasing, is going to be towards it, okay? So let's now just utilize table 10.4 to actually understand the rest of the statements for the Le Chatelier's principle. In letter 1C, it says oxygen is added to the system. So what letter does that refers to? Oxygen is added to the system. Excellent, we're adding product. So this again is letter C. Let me just choose colors for A and D. So at this time, I want you guys to take a moment, read the statements on problem 2, and select the correct letter from table 10.4 that will explain in terms of what kind of stress each of those statements are representing. So I'll give you guys 2 minutes to do that. So let's go through problem 2. When we decrease the concentration of dihydrogen monosulfide, what letter does that correspond to? We're decreasing Great job. We're decreasing a reactant. When we are increasing the concentration of hydrogen gas, what are we doing? Great job. We're adding product. Increasing the concentration of methane. Next, decrease the concentration of carbon disulfide. Lastly, we are decreasing the concentration of hydrogen gas. Great job, you guys. Now, if you're utilizing table 10.4, it's easy to, or I should say, is less difficult to identify what is the type of stress. Remember that once you have identified the type of stress, then you can go along the lines and say what kind of change it is, or what is the shift in the direction of the reaction. So as long as you know how to utilize table 10.4 by identifying the stress, then finding the change in the reaction rate and the shift in the direction of the reaction is all given in the table. Any questions on how to apply table 10.4 to problems with Le Chatelier's principle? Now let's move on. Oh, there's a question. Go ahead, Francisco. Okay. Then let's move on to the next topic in chapter 10, which is the idea of the dissociation of water. So in the world, there are a selected number of molecules that are considered amphoteric molecules. And what defines an amphoteric molecule is that any molecule that is amphoteric, it can act as an acid or it can act as a base. That's what defines it. So any molecule that can act as an acid or a base, it is known as amphoteric. Water is one of those molecules. As I told you guys, water is a molecule that is very special. Its properties compared to other molecules that are composed of things that have about the same atomic mass, like water behaves very differently, okay? So what this means is that if you have water molecules sitting in a container, and understand that these reactions are super fast, okay? Water, since it can act as an acid and as a base, it is known that water, as you can see in the bottom left side of the slide, when it's acting as an acid, it's going to donate a proton to another water molecule. And when it does that, now we create H3O+. Remember, H3O+ is called hydronium. When the water molecule loses its proton, then it's going to create hydroxide. Now, when you guys are drinking water, or when we have water at home, no, you're not drinking hydroxide ions and hydronium ions, okay? Because this reaction is in equilibrium. And in all honesty, it goes back and forth, back and forth, back and forth. To trap it on one side versus the other, okay, there has to be other things that are taken into consideration, and water molecules exist as what we see in the reactants mostly. Just because hydronium and hydroxide are not going to be the prevalent species that we have in a container with purified water. That being said, utilizing the concepts of and the ability of our water to be amphoteric in the laboratory, scientists started understanding how this relationship of water being amphoteric, acting as an acid or acting as a base, it actually can be related to the behavior of some molecules, okay, in general. So in studies in which water was being studied, we saw that specifically we can see instances in which there are a little bit different, or there are different concentrations in that hydronium and hydroxide, or when hydronium and hydroxide are at the same concentration. So those studies of water was what gave rise to understanding what is an acidic solution versus what is a neutral solution versus what is a basic solution. So understand that the difference between these three different types of solutions is that if you have an acidic solution, then your concentration of hydronium, or in other words, your concentration of proton is higher compared to hydroxide. Because understand that in general, since hydronium, which is H3O+, it's going to be a source of protons. At times, we say that that is the same thing as saying the concentration of protons. So again, in an acidic solution, your concentration of hydronium ions is going to be higher compared to hydroxide ions. If we have the same concentration of hydronium and hydroxide, again, in terms of water, then that means that we have a neutral solution. And lastly, if your concentration of hydroxide is higher than the one in hydronium, then that is said to be a basic solution. So all of these concepts were there incorporated into the definition of what pH is, okay? And understand that pH is a scale. pH does not have units. It's going to give you a numerical value, and that numerical value is going to indicate the acidity of a solution. pH, since it's defined by the amount of protons in a solution, understand that that's why when you are comparing different pHs, as you can see in the bottom of the slide, you know, pH lower than 7, pH equals 7, pH higher than 7. We are specifically looking at hydronium, or in other words, proton concentration in a particular solution, okay? So understand that many of the substances that you are exposed to in everyday life have a particular unit in terms of pH. So when we look at the figure here on the right side of the slide, we can see the things that are acidic. Anything that is acidic is going to have a pH less than 7. So as you can see, vinegar is acidic, soda is acidic, oranges are considered acidic, tomato juice, coffee, even a potato, okay? Bread is considered acidic. Milk is considered acidic, okay? This was one of the questions that I asked you guys in the beginning of the semester when we were doing that chemistry trivia. Milk is actually slightly acidic. When it comes to things that are neutral, we know that purified water, okay, has a pH of 7. Now, drinking water, because it has a pH of 7.2, is slightly basic, okay? The blood, even our blood, has a particular pH. On average, it's 7.4, okay? And that is a very important number, because the pH of our blood needs to be at 7.4 in order for the biochemical reactions that happen in our body to be occurring normally. If the pH of the blood is not 7.4, you can get sick. But as you can see, on the basic side of things, on things that are considered bases, we have detergents, seawater, products like Windex, which has is a solution of ammonia, bleach, is actually basic. And here we have a 1 molar solution of NaOH. So when you're buying Drano, okay, that's pretty much a base. That's why you have to, you know, be careful with it. We will be talking about alkaline water. There's a question in the chat of what is my opinion about alkaline water? And I will tell you my opinion once we, you know, finish all of these discussions, because we will talk about it at the end of the chapter. So understand that when we have something according to the pH scale, at 7 is neutral, lower than 7 is acidic, higher than 7 is basic. We have instruments that measure pH, okay? And you can see them illustrated here. So the first one is a pH meter. So this instrument in the laboratory has a probe, and the probe is going to be this part of the molecule, or sorry, this part of the instrument. Oh, let me use a different color. And in this probe, there is a detector down here. In this detector, when you have calibrated your instrument with some pH standards, you're telling the machine, hey, these are the standards for pH 3, pH 7, pH 10. It depends how many calibrations you need to do. Then you can actually dip in your solution the probe, and then once that end of the probe, it touches the liquid, in the screen, it will tell you what is the pH of the solution. So in this solution that we have in the beaker, because it has a pH of 4, is it acidic, basic, or neutral? Let's put it in the chat. Great job. It's acidic because the pH is 4. Now, put a 1 in the chat if you have used pH paper, which is what we have in the illustration for letter B. Excellent. There's a number of you that have used pH paper. I think pH paper is one of those things in the laboratory that if you have taken general chemistry or other chemistry courses is it's available, okay? And it's relatively inexpensive. So what is pH paper? pH paper, it is a paper that has been coated with a dye that when the dye touches a solution, it's going to adopt a particular color, okay? And you can see here when we zoom in that this pH paper specifically can look at things all the way from pH 1 to pH 11. And on the container, you can see the different color ranges that the pH paper can turn, and based on the change in color that the pH paper gives, then that can tell you what is going to be the relative pH for the solution that you're studying, okay? So this is not exact, and pH paper can actually be with different ranges. It's just that this one is more of like a general pH paper, okay? Then we have letter C. Put a 2 in the chat if you have done experiments with purple cabbage juice. There you go. There's a couple of students that have done that. So when it comes to purple cabbage juice, what makes purple cabbage have its color is called a flavin, okay? This flavin, which is a biomolecule, is going to, similar to what we saw with the pH paper, do color changes depending on the pH of a particular solution. It is typical that at times when you're working with purple cabbage juice, this is something to do safely at home. You can watch YouTube videos on it. And literally what you do is that you buy purple cabbage, you boil it, and then that liquid that comes out that is purplish, please utilize distilled water if you use it at home. Don't use tap water, because tap water has a different pH than purified water. If you use tap water, your purple cabbage juice will be the color that you see in that beaker. If you use purified water, then it's going to be purple. So when this happens, then you can actually test around the house what are the pHs of some of the products that you have, like detergent, like shampoo, like conditioner. And in the laboratory for Chemistry 104, when we're face-to-face, that is one of the labs that we actually do. So students understand what are the pHs of household items, okay? When it comes to the transition of colors for purple cabbage juice, understand that the colors that are in this range is going to be acids. This is going to be neutral color for the purple cabbage juice. And this is going to be if you're dealing with bases, okay, in terms of the solution that you're trying to explore. This is a very fun experiment. And usually if I have, family gatherings with, friends and family, and the kids want to do a quick experiment and see things turn different colors, this is the experiment that is my go-to, because I consume cabbage, so I do have purple cabbage juice around. So now let's actually go through calculations for pH. So when we are calculating pH, we need to understand that pH is defined by the following equation. pH equals the negative log and that log is going to be base 10 on the concentration of hydronium. Now, understand that for the purposes of this, having the concentration of hydronium is the same thing as having the concentration of H plus, okay? So when you are doing problems, if it says hydrogen ion concentration or hydronium ion concentration, we are referring to the same thing. Now, let me mention that when it comes to logarithmic equations, there are a particular set of rules for Sig Figs. Now, for Chemistry 104, I don't stress my students with the Sig Fig rules for logarithmic problems, but understand that if you have to take other chemistry courses, you have to understand that there's actual specific rules when you have logarithmic problems in an equations, okay? So to calculate pH, the main thing that I want students to know is how to actually enter these values into their calculator. If you do not understand how to enter these numbers on the calculator, after class, I will be more than happy to teach you how to utilize your calculator to actually enter these numbers and get the results, okay? Now, understand that when we are looking at these concentrations of H3O plus, or it could be of hydroxide ions in a solution, they are going to have a power 10, okay? Now, for measurements in which you have a coefficient of 1.0 times 10 to a negative value, okay, only for measurements that the coefficient is 1.0 or 1.00, okay, then it is easier or less complicated to find the pH value, okay, because the exponent that we have in the power 10 corresponds to the value of pH. So for example, if you're trying to do the equation and trying to find the pH of a solution that has a concentration of hydronium ion at 1.0 times 10 to the negative 2, the pH of that will be the positive value of that exponent. So the pH of that is going to be 2. Now, you guys can see that it is 2.00. I'm going to show you the Sig Fig rules, but I'm not going to test you on the Sig Fig rules. When it comes to these problems in the exam, I say in the instructions, express your pH units in this number of Sig Figs. So you guys don't have to think about, oh, what value should I put? Make sure that you read the instructions, okay? So for those students that have other chemistry classes, the reason why this value is 2.00 is because the Sig Fig rules, okay, for logarithmic equation establish that if this has 2 Sig Figs, meaning your concentration of hydronium, your concentration of hydroxide, your concentration of hydrogen ion, then pH must have 2 decimal places, okay? As you can see, it's a mouthful. You have to look at the Sig Figs, but then that's transferred to decimal places. That's why I don't want you guys, you have enough things to worry about in this class with other concepts. When it comes to Sig Fig rules and pH, I don't want you guys to worry about it. So make sure that you read the instructions into what number of digits, and remember that you have to round, you need to express your pH units. But again, I just wanted to show you guys what are the rules for those students that have other chemistry classes. So at this time, let's actually go through understanding how do we deal with pH equations or the calculations for pH. Any questions before I start talking about these? then let's get started. When it comes to the equations for pH, you guys are going to have three main equations. The first one is the one that I introduced a moment ago. pH equals the negative log of the concentration of hydrogen ion. Remember, H plus concentration is going to be the same thing of H3O plus concentration. Okay. If you are given the pH, you can find the concentration of H plus by, in your calculator, taking that value of pH in a negative form and raising it to power 10. The third equation that we see here is going to be that if you multiply the concentration of proton and the concentration of hydroxide, that is going to equal 1.0 times 10 to the 14, because experimentally it was shown that that is going to be the concentrations. So this is just a standard. So when you multiply these two things, it equals, for a neutral, in neutral conditions, it was determined that this was the case, okay? Now, equation number 3, we can actually separate into two. So I'm going to call this 3A and 3B, okay? So utilizing this equation, I can say 1.0 times 10 to the negative 14. If I divide it by the hydroxide concentration, that can give me the concentration of proton in my solution. Or if I'm trying to find the hydroxide concentration, I can take 1.0 times 10 to the negative 14 and divide it by H plus. And that's going to give me the concentration of hydroxide in a particular solution. So it depends on the question if you're going to use equation 1, equation 2, 3A, or 3B. Let's go through a few examples to understand how we're going to utilize these equations to solve the problems that you guys are responsible for knowing for the exam. Let's go through problem 1. It says, if the H plus concentration is 2.1 times 10 to the negative 12 molar for perchloric acid, what is the pH? Okay, so in problem 1, we were given the H plus concentration and we're trying to find the pH. Let's put in the chat, what equation do I need? 1, 2, 3A, or 3B? Excellent. We are calculating pH, so we need equation number 1. Equation number 1 says that pH is going to equal the negative log of 2.1 times 10 to the negative 12 molar. So when we have our calculator, we will say 2.1 times 10 to the negative 12, and then we're going to take the log of it. That's going to give us a negative value, but that negative value, we can actually turn it into a positive value, because remember, negative times negative is positive. So if we go by the rules of Sig Figs, which that's what you're going to see in the answer key, just because, again, for those students that are going to take other chemistry courses, because this has 2 Sig Figs, your final answer for pH needs to have 2 decimal places. Okay, so when we round our answer to 2 decimal places, what is the answer for this? What did people get? Excellent. That's what I also obtained. So it's 11.68. Is this an acid, base, or neutral? What kind of solution is this? Acidic, basic, or neutral? At a pH of 11.68. Excellent job. It's basic. Let's go to number 2, another pH calculation. But in this pH calculation, what was given to us is OH. Okay? So if you get OH, then there are 2 equations that you need to use. Okay? So when you're given OH, there's 2 equations that we need to use. What is the first one that we need? Excellent job. We need 3A. Because 3A is going to give us the concentration of proton. Once we have the concentration of proton, then we can use which equation to find the pH? Not 3B, not 2. Thank you, Alexa. Number 1, okay? Let me illustrate. So first, we're going to use equation 3A. Because since we are giving hydroxide, we can calculate H+. Okay? We do 1.0 times 10 to the negative 14 divided by 5.9 times 10 to the negative 1. You get a calculator display of 1.69, and I'm going to put 3 dots because we need to use all of the numbers, times 10 to the negative 14 molar. Then we are going to use equation 1. We're going to say, oh, I'm calculating pH, and since I have the concentration of H+, I can say negative log of 1.69, I'm putting the 3 dots because there's more numbers in my calculator display, times 10 to the negative 14. So again, our measurement started with 2 Sig Figs, so technically we need to put this to 2 decimal places. When we round our answer to 2 decimal places, what will be the answer? So when we take the negative log of that 1.69 times 10 to the negative 14, Gina, go ahead with your question.
For the negative log, how am I entering that into the calculator? Because I can just put log, but when I put negative, it doesn't allow me to put the negative before log.
No problem. That's what I said, that at the end of class, for those students that need assistance with understanding how to word their calculator, I'll be able to help you.
Okay, sounds good. Thank you.
No problem. So what value did you guys get? That pH. I didn't get negative 14. Thank you, Giselle. Thank you, Adeline. This is 13.77. Remember, pH doesn't have a unit. It's just a scale. So is this acidic, basic, or neutral? Excellent. It's basic. Okay. Any questions on problems 1 and 2? And again, I will help anybody that needs assistance with the calculator. I understand. I will help you. Then let's go to problem number 3. It states, what is the hydrogen ion concentration of a solution of pH 8.25? So I need to find hydrogen ion concentration and I'm given pH. So which equation do I need? Great job. We need equation 2. Because this is the main thing about this, that you need to understand, if I'm given the problem, let me interpret what is asked of me, and then what is the equation that is attached to this problem. This is why I'm going through it. So because once you understand that, it's a matter of like entering it correctly and getting the number. So when it comes to this hydrogen ion concentration, like you guys said, we're going to do H plus is 10 to the negative pH. So that means that we're going to do 10 raised to the negative 8.25 power. Okay. And because pH has 2 decimal places, basically, we're going to give this value as 2 Sig Figs in the coefficient. Again, for those students that are like, do I need to know Sig Figs? You don't, you guys. I will tell you how many Sig Figs I want, but I just need to practice for the students that are going to take some of this information further. So when we express this number, it has to be with 2 Sig Figs in the coefficient. What is the answer for this? That's not correct. That's not correct. People are not. It's 5.6, correct. 5.6 times 10 to what? Because 5.6 is the coefficient. What is the whole value? For the concentration of H plus. So that is the coefficient, 5.6 times 10 to what? Excellent, 5.6 times 10 to the negative 9. And the unit is molar. Okay. Again, the reason why we have these 2 Sig Figs is because our pH has 2 decimal places. Again, these notes is for the students that need it. That negative 9 came from the calculator. 8.25 negative, and then 10 to that. Make sure that your calculator, whenever you're doing concentrations, is in scientific notation. That is something that we can address when I show you guys how to work your calculator. Because for those students that don't have their calculator in scientific notation, it will show you something that is 0.000006. How many zeros are here? 1, 2, 3, 4, 5, 6, 7, 8. It's 8 zeros before the 6. But when you change it to scientific notation, that's the value that you see. It's 5.6234, a whole bunch of other numbers times 10 to the negative 9. Let's at least continue the next 3. What if we have a pH, okay, of 10.3? We're doing the same thing as number 3. What will be the value? So again, question 4, we're utilizing the same equation that we used in question 3. The concentration of H plus equals 10 to the negative 10.3. And because its concentration is going to be in molar. What is the concentration of H plus if your solution has a pH of 10.3. Excellent. That's what I got also. Let's do number 5 together. Okay. In number 5, it says determine now hydroxide concentration, but I have the pH. Okay. So if I'm given pH, but now I'm interested in hydroxide of that solution, then we need 2 equations for that. Okay. We need equation 2 followed by equation 3b. Let me illustrate. So equation 2 is utilized because we need to first get proton concentration. So 10 to the negative 5.22 will give me the concentration of H+. Awesome, I'm glad to see that people are figuring it out in the calculator. Excellent. So this is 6.025 yada 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 times 10 to the negative 6. Remember that those 3 dots is because my calculator display is bigger than this.
So we wouldn't do the Sig Figs, Professor, not yet.
No, it's at the end. Remember that for this, I don't want you guys to even think about the Sig Figs. When it comes to this, I usually, if you guys to do numerical entry, I make you guys do the pH only. Formatting things that are in scientific notation, it is a pain to do on Canvas. So typically the questions are, you know, calculate the pH, and then I give you different things. You can calculate pH from H+ concentration, from OH- concentrations. So that's typically what I do for you guys. If it comes to doing calculations like this, sometimes I give them in multiple choice, just because, you know, formatting exponents and Canvas, it can be a pain. So I'm just writing all of this just because, you know, right now I'm just taking all of the numbers. So typically when we do is that we apply Sig Figs at the end. So once I have this number, then in order to get OH concentration in my solution, then I'm going to use equation 3b, which says that the OH concentration is going to be 1.0 times 10 to the negative 14 divided by the number that we obtained from using equation 2. Okay. Now, again, this is for other classes. Since this has 2 decimal places, basically the answer needs to be in 2 Sig Figs. So when I take 1.0 times 10 to the negative 14 and I divide it by that large number, and we rounded to 2 Sig Figs in the coefficient, what did you guys get? 2 Sig Figs, not 2 decimal places. 1.0 1.7 times 10 to the negative 9 molar. Any questions so far on any of the equations that we have utilized for solving these problems? So what I was mentioning, there's a question in the chat about Sig Figs. So what I mentioned is that you need to read the instructions for the exams. For my students that need to take other chemistry classes, I'm just putting here the Sig Fig rules for logarithmic equations. Because if you have to take chemistry 110 and even chemistry 115, because of your educational path, then the rules for Sig Figs in exponents will come up. But for the purposes of this class, please read the instructions. And in the instructions, it will tell you how many Sig Figs to utilize for your answer. And remember that you need to round, because rounding is one of those things that sometimes students forget unless you're prompted. It says round to, no, remember, rounding is implied. You always round. Let's do the last problem, which is, what is the hydroxide concentration in an aqueous solution that has a hydrogen ion concentration of 2.70 times 10 to the negative 2. So if we want hydroxide and we have hydrogen ion, which equation am I going to use? I want hydrogen ion, and what I was given is hydroxide. It's not 3B. Oh, wait, it's, yes, sorry, read it incorrectly in my head. So yes, we need 3B because we were given hydrogen ion. So we want hydroxide. So we're going to do 1.0 times 10 to the negative 14 molar divided by 2.70 times 10 to the negative 2 molar. So how much hydroxide do we have in this solution? So we need to, since this has 3 Sig Figs, we need this in 3 Sig Figs. So when we round this to 3 Sig Figs, is 3.70 times 10 to the negative 13 molar. Okay, so you guys have to be familiar with the use of equation 1, equation 2, 3A and 3B for pH calculations or concentration of proton or concentration of hydroxide. Any questions? Then let's move on to the next concept, which is buffers, okay? So buffers are going to be solutions that resist changes to pH when you have added acid or added bases, okay? In our body, understand that hydronium or hydroxide that may be present in food and cellular processes are processed through buffer systems. We have several buffer systems. We have about 5 of them. The most important one is the blood buffer system, which we are going to talk about in class. Now, the buffer system that we have in our blood is based on carbonic acid, okay? But it maintains the pH of 7.4 in our blood because of the biochemical reactions that are actually working under those pH conditions, okay? Now, understand that the pH of our blood is actually affected by respiration. So changes in the intake of CO2 or release of CO2 in the body can affect that pH. Now, let's look overall, at least in the figure that we have on the right side of the slide, how or at least illustrated, how a buffer system can resist changes in pH. As you can see on the top of the figure, we see that we have just water. And if you add acid to just water, then you have more concentration of H3O+, so the pH is going to drop that drastically. And let's say that it drops to pH of 4.0. Now, if you have a brand new beaker of water, okay, and then the instrument here is just a pH meter, but you add base, okay, then that base is going to increase the concentration of OH+ in your solution, so the pH is going to increase, okay? And for example, here we're illustrating it as a pH of 10.0. But if instead you have a solution that has a buffer, it doesn't matter if you add acid or if you have base in it, okay, depending on the buffer capacity of your buffer, but you can see that the values for pH is going to stay close to the pH of the buffer. And that is their role, okay? Your buffer is going to resist changes in pH, and on average, you will have a pH that is close to the pH of the designed buffer. So the first thing that we need to establish is, how do we make a buffer, okay? And this is the combo for buffers, okay? You need, for making a buffer, a weak acid. This is why it's important that you guys know what is a weak acid versus a strong acid. And then that weak acid, you're going to add in equal amounts with the salt of its conjugate base. This is why it's important that you know how, if you have a weak acid, determine the chemical formula of its conjugate base. And what makes it a salt is just pairing it with a metal. So for example, here we have acetic acid. The conjugate base of acetic acid is going to be acetate. The salt of that conjugate base will be if, for example, we pair this with sodium. So sodium acetate is the salt of that conjugate base. And remember that we need to add them in equal concentration. So in problem 10.53 from your textbook, we have pairs of molecules. And in the exam, you have to do a problem similar to this. You're giving pairs of molecules, and then you have to tell me if this makes a buffer or it doesn't make a buffer. Remember, in order for us to have a buffer system, we need to have a weak acid plus the salt of its conjugate base. Okay, let's look at the first pair, NaOH and NaCl. Let's use this chat. Do we have an acid? Yes or no? NaOH and NaCl. Do we have an acid? It's 50-50, you guys. Do we have an acid? Yes or no? Look at the two formulas, NaOH and NaCl. What is the acid? There's students that are saying yes. Is NaOH an acid? So let's say it again. Do we have an acid if we have NaOH and NaCl? Great. This is why it's important that you guys know what is an acid and what is a base. We don't have an acid. We don't even have a weak acid. We have a strong base and a salt. Look at the definition for buffer system. Can a strong base and a salt make a buffer? Great. Thank you for the nose. This is not a buffer. This is a strong base. This is a salt. Remember that salt is another word for ionic compound. Let's look at the next combo. Carbonic acid and sodium bicarbonate. Do we have a weak acid? I agree with Daniela. Everybody should be agreeing with Daniela. Yes. Daniela, what is the weak acid in it? Just write the chemical formula in the chat. What's the weak acid? What's the chemical formula? Great job, H2CO3. So this is a weak acid. Now, here we have sodium, and it could be lithium, it could be potassium, okay? So understand, as long as you have a metal. The next one, HCO3 minus. So if I separate this into ions, this is Na plus, HCO3 negative. Remember, salt of conjugate base. If this is HCO3 minus, the conjugate base of carbonic acid, yes or no? Is HCO3 minus the conjugate base of carbonic acid, yes or no? Excellent. So here we have a combo for an acid. I'm sorry, a combo for a base, for a buffer, is what I'm trying to say. So this is a buffer because we have a weak acid and we have the salt of its conjugate base. What about HF and KF? Do we have a weak acid? Yes or no? In HF and KF, do we have a weak acid? Yes, excellent. I see a lot of yeses. From my people that said yes, what is the weak acid in that system? Great job. So this is a weak acid. Now the next question is KF minus the salt of the conjugate base? I don't like those no's. K plus, F minus. Let me ask a similar question. Is F minus the conjugate base of HF? Remember, if your conjugate base is paired with a metal, that makes it a salt. So letter C is a buffer. Question so far. You need to be able to identify what is a weak acid, and then its pair needs to be the salt of the conjugate base. Go ahead, Thea.
So I understand like the weak base and everything, but the second part is the one that gets me confused. So are we supposed to be breaking it down as if it was like an equation, like we did earlier, where we figure out the base and acid and then conjugate base and then acid?
So the reason why I'm breaking apart the second component of the buffer is because I'm trying to remind you guys that the second component is a salt. So it is an ionic compound. Ionic compounds form cations and anions. And what I'm trying to illustrate to you guys is that the anion is going to be the conjugate base of the weak acid if we have a buffer. So that's why I split it like that.
So the conjugate base for HF would be F because it's losing a hydrogen.
Excellent. Yes.
I wanted to make sure because it's just like I was confused with like I said, the concept was like the reason that's a conjugate base is because it's lost the hydrogen. That's why.
Exactly. So this is just tying together what we did before. Thea, does it make sense?
No, I'm so lost.
I know, I
Okay.
get it too.
No problem. So what part are you, let's just find each other. What part is it confusing? Why I'm breaking into ions, the next one? The second portion?
I think it's because like in my mind, I am stuck with like when you say salt, I'm thinking it has to have an NaCl. And then and the potassium fluoride doesn't have an NaCl. So I'm like, where did the salt come from?
Okay, so let's just define something. So right now we're going to erase from your brain that salt is NaCl. Table salt is the only one that is NaCl. Any ionic compound, that's what a salt is. What makes an ionic compound? Metal, non-metal. Metal, polyatomic ion. So just register now in your brain that I need to have in this combo a weak acid. So once you identify the weak acid, and then the conjugate base of that weak acid, and it's going to be paired with a metal because that makes it an ionic compound, and ionic compounds are known as salts. So remember, table salt, that is sodium chloride, but why is it called a salt? Because it is an ionic compound, okay? So for example, let's look at D. Do we have an acid? Yes or no? Excellent. We don't have an acid. We have two things. What are those two things that we have together on letter D? Great job, you guys. Salts. KCA is a salt. NaCl is a salt. Why? Because they're both ionic compounds. So this is not a buffer. Let me just throw two more examples to you guys. We have H3PO4 and NaH2PO3. Okay. Do we have a weak acid on E? Let's put the chemical formula of the weak acid. What is the chemical formula for the weak acid? Excellent. This is your weak acid. Now, the question is the pair that I have in it the salt of its conjugate base? I see a no and I see a yes. Yes, we are divided. I see yeses. I see yeses. I didn't make a mistake. I agree with Francisco. NaH2PO3 is not the salt of the conjugate base for H3PO4. H3PO4, if it loses NH+, what is the chemical formula? Just put it in the chat. I need you guys to pay attention to this. Excellent. H2PO4 -1. Is that? So that's not a buffer. I'm not trying to be tricky. I'm trying to train your eyes.
But didn't you say that ionic compounds so a salt is a metal plus a non-metal, or a metal and a polyatomic ion, right? So that has a metal, which is a sodium, and then a polyatomic ion, which is the H2PO3. No?
But
Or
like
the
it says in the chat, thank you, Elle. The question says NaH2PO3. We didn't start with phosphorus acid. We started with phosphoric.
Oh, okay.
It
Okay,
has to
I
be
see.
the salt of its conjugate base. These little mistakes are the ones that then students are like, oh, but her exams are tricky. No, I'm trying to see who masters the concept versus who is just going by and not understanding what's happening. They're just, looking overall. So I want all of you guys to be masters on this. Because what I want you guys to click is that if I identify this is the weak acid, I already learned in the beginning of the chapter how to write the chemical formula of its conjugate base. Once I have the chemical formula of its conjugate base, it's going to have sodium, lithium, or potassium in front of it. So I need you guys to be careful when it comes to these. So this is not a buffer. What about letter F? Is that a buffer? Do we have a weak acid? It is. Great job. Because this is a weak acid. If we have H2C2O4, the conjugate base of this is HC2O4 -1. And look, HC2O4, HC2O4, and I have potassium in the beginning. So this is a buffer.
In the list of like common strong and weak acids, that's not listed. Does that matter?
Of course, because I taught you guys, this is why out of that list, and thank you for bringing it up. I told you guys from this, look at what I highlighted, not the strong acids. Because if you know the strong acids, anything that is not in the top 6 is a weak acid. And guess what? Any polyatomic ion that you guys have learned so far, if it starts with a hydrogen, it depends if it makes the list of the top 6 or not. I can make a weak acid out of that. You can have the thiosulfuric acid, which is not in this list. You can have oxalic acid. You can have permanganic acid. So understand that the acids that are listed here as weak are not the only ones that I can use. it is important that for this exam, you guys are able to organize yourself and understand the concepts. There's a lot of material, but I know that you guys can do it. Any questions about determining if two molecules given forms a buffer or not?
So really, like on your question for F, we should be looking at like that acid and then break it down when it loses a hydrogen ion. And then if it matches the second polyatomic ion, then really that's a buffer. It doesn't really matter if it has a potassium and a sodium or whatever the element it is before that polyatomic ion, right?
Correct.
Am I following?
Yep.
Okay.
Yes, yes, yes. And then remember that you need to, the main thing is like, can I identify the weak acid, right? Because what if, for example, let me just do one more, and I want to finish the concepts of this chapter so we can go on break. Let's say that I have HCl plus NaCl. Okay. So letter B for buffer or NB for not a buffer. HCl and NaCl. Ooh, I'm liking these answers. Remember that when it comes to these, they are both going to look like neutral compounds. So for my students that answer not a buffer, you're correct. Why is this not a buffer?
Because it doesn't have a conjugate base. HCl.
It does.
No. Yes.
HCl is a strong acid.
Thank you, Alexa. Yes. HCl is a strong acid. How do I know that HCl is a strong acid? I know, or I look at this table, look at HCl right below perchloric acid. So again, my definition of a buffer is weak acid, salt of its conjugate base. Going to your question, Gina, if you have HCl and HCl lost an H plus, it makes Cl minus. Cl minus is here. Is paired with Na. So if you're not careful and you don't understand the definition, it would be like, oh, acid, that is the salt of its conjugate base, done. But the thing is like, if you don't know that HCl is a strong acid, then you can get caught up in not understanding fully the definition.
Yeah, I get it, Professor. Like I said, I told you it's the math is easy. The math, no, I'm not saying it's easy. It's the concept, because I get it. Like I'm in my mind, I'm looking for. I just gotta slow down, I guess you could say. Gotta slow down.
Yes, you have to pace yourself. Like that's the thing about specifically exam 2 that I tell students, like exam 2, at least on you guys' end, should be completed around an hour and a half, an hour 45. Like that's the type of exam that I will be writing. Then you should have at least a solid 30 minutes. For if you take a little bit longer, let's say 2 hours, but at least you should take 30 minutes to make sure that you enter your answers correctly. It requires organization. It requires that you have all the material in front of you. and you know how to use it properly. Remember that when it comes to the exam, similar to the first exam, the first 10 questions is chapter 6. Then you switch. The next 10 questions is chapter 7. You switch. Next 10 questions is chapter 9. And lastly, the last 10 questions is chapter 10.
So for the exam, there's going to be a total of 40 questions, 10 questions for every chapter, 6,
Yes.
7, 9, and 10.
So remember, I say items because, for example, naming, when you guys are naming, is not, oh, what is the name of this? No, it's like, I give you 5 chemical formulas and you have to type in the name correctly with the correct format. That's why you guys have practice in the chapter quiz. You have practice in the lab. You have practice, hopefully, in the extra credit. So by the time the exam comes, you won't be scrambling, be like, how do I format this? No, you already, if you practice before, you have the system down of like how you're going to enter these answers. So that's why I encourage you guys to practice before the exam. Don't let the exam be the first time you see this material. So that's why I encourage you guys, do the best you can to, do as much work as you can before the exam. You, again, don't want the exam to be the first time that you see this material. Or if you don't have organized notes, that all of a sudden this is the first time that you're scrambling of like, which presentation, which notes, what rules do I need, when? You don't want the exam to be that time, because the 2.5 hours are going to go by very quick. So plan in your head, okay, I should be, and it's pressure. Hey, I understand. I should be done with the 40 questions around 1 hour 45. If you're done earlier than that, great. But make sure that you check what you have entered. And don't second guess yourself too. Just be careful entering the answers. Understand the format.
Professor,
So yes, go ahead there.
sorry, I have a question. Okay, so just to simplify this in my head, if we're looking for a buffer,
Yes.
and like in the thing that we're doing right now, if it's not a weak acid, then automatically we're saying it's not a buffer.
Exactly.
Exactly. Then if we find out that it has a weak acid, then really that second formula, we're breaking it down where it loses a hydrogen ion. If it loses a hydrogen ion and it matches that formula, then really it is a buffer.
Correct.
And
that's a good
further,
strategy for doing this problem in the exam.
And then furthermore, trying to find out the strong acid, if it doesn't belong in that table 10.3 top part, those 6 elements that we talk about, or 6 polyatomics that we talk about,
No, it's just 6 molecules. Let's just call them, that's the correct term, molecules.
So if it's under that table 10.3, if it doesn't belong in that 10.6, sorry, in the 6 molecule, then we are assuming it's a weak one. It's a weak acid.
Mm-hmm.
Okay.
Yes.
There is a lot of steps when it comes to finding something in the test. Like just what they explained, that's only on one problem.
Yeah, but that's why I mean with you guys that you need to organize, because that's one of the things that sometimes it doesn't click in chemistry with people until they are towards the end of the semester. Like for this problem, just like Thea explained it very well. If you have to find a buffer, click in your brain, oh wait, I need to answer this question in my exam, I need this table. And if I see in the combos any of those 6, my answer is going to be not a buffer. That same, that process of thinking will save you a lot of minutes, because if you are like, oh, how do I determine if it's a buffer or not? No, you're thinking, just like, it was explained a few moments. Oh, for buffer, not buffer, I need table 10.3. And any of my combos that have any of these, that's not a buffer. any combo that has a strong base, meaning something with OH, is not a buffer. Now, if I have my weak acids, then I have to do one more step. Let me determine the conjugate base. And let me see if that second compound has the conjugate base of my first one. And then in the beginning, it's going to be sodium, lithium, potassium. That's the work. So see, like that thought process is the same. But you have to, you know, have it clear in your brain, like, this is my strategy for this problem. This is something that we can discuss tomorrow in the review. Like, how do I strategize this type of question? Because I think it will help for those students that right now have, you know, just too much information and they don't know how to compartmentalize it. Once you have compartmentalized of like, this problem requires this strategy, this problem requires this other strategy, your life will be easier. So I announced in the beginning of class that tomorrow I will be available at 9 a.m. and I will be putting it also in the announcement. So I'm going to have a special review session for those students that can come and are able to join us. So again, we are going to be reviewing the material for the exam starting at 9 a.m. I think it will take us a couple of hours to answer questions, and you know, it's not a review that I give you the answer for the exams or none of that, because sometimes, you know, I don't understand where people get these ideas. This is just going to be service to you guys. So just like we explain, if you need to be like, Dr. Luz, explain to me, how do I read this and what do I need? Just like we explained for the buffer, not buffer, we're going to do that. So I want to finish up chapter 10 so we can go on break and then do the Kahoot. The Kahoot has 30 questions. So let me just finish up the material, okay? So in this slide, we are explaining how is that a buffer works and how does it really do its job, okay? So as you can see, in the middle is the buffer system, okay? We have a weak acid and its conjugate base. And there was a question in the chat of like, does that conjugate base is going to be negative charge? Well, remember that is going to be an ionic compound. So let's say that it is with sodium, okay? When we look at the arrow that is pointing towards the left, this is the case where we add acid to the system, okay? When we add acid to the system, as you can see, you'll be like, wait, there's an increase in weak acid. Why is that? Okay. As you can see in the words down here. So this, when you add H3O plus to the buffer, this component of the buffer, which is the salt of the conjugate base, okay, reacts with the incoming acid, okay? So if we think about it, when we add acid to the system, what we're doing is that now, since this is added acid, that means that we are adding H plus, and that H plus is reacting with my conjugate base. And the product of that reaction is H2 is HC2H3O2. So this is the chemical formula of this. So the outcome of it is an increased concentration of the weak acid. Put a 1 in the chat if that makes sense. Put a 2 in the chat if I have to repeat it. I'll repeat it. So we're starting here, my buffer system. I added acid to the buffer system. That means that we are putting H plus into my buffer. Out of the 2 molecules in my buffer, the conjugate base is the one that reacts with that acid and it makes more weak acid. That's why I see an increase in the concentration of weak acid. Put a 3 in the chat if that's solidified in terms of like, if I add acid to the system, which one of the 2 molecules is the one that reacts with the incoming acid? Let's see what happens when we add base. When we add base, adding OH, then what happens is that there's a neutralization reaction with the weak acid. So when we start with a buffer and we add base, my neutralization reaction is that H2, I keep on saying H2, HC2, H3, because this is an acidic acid buffer, O2 is going to neutralize with OH minus. So we are going to make C2, H3, O2 minus plus water. So here, since we are making this, that's why we have an increase on the concentration of conjugate base. Put a 4 in the chat if the case of the base system makes sense. Put a 5 in the chat if I need to repeat this. So in the case of a base, we have a buffer system. We're just focusing on this area of the molecule. I start with a buffer. I add base to it. Which one of these 2 is going to react with that incoming base? As you can see here, the weak acid is the one that reacts with that incoming base. The product of that reaction is going to be more conjugate base. That's why we see that the bar for the conjugate base is increased. Put a 1 in the chat if now the case of the base makes sense. Go ahead, Gina.
So to get the concept solidified, we're looking at, so if we're looking at adding acid, the acid reacts with the base to make more weak acid, and then to add base, interacts with the weak acid to make more conjugate base, right?
Correct. Excellent. Now, why is all of this important? Because this whole buffer system, we have it inside of our bodies, okay? We have not the acetic acid, we have what is called the carbonic acid buffer system. This is the one that is in our blood, so that's why it's called the blood buffer system, okay? In our blood, we have carbonic acid, and carbonic acid breaks into giving just protons and its conjugate base, which is bicarbonate, HCO3 minus, okay? Now, going over the question that was a little bit earlier today, What is my opinion about alkaline water? Alkaline water, at least in my experience here in California, is very popular. When it comes to alkaline water, there is no scientific evidence to date that alkaline water is good for you. No scientific evidence. There hasn't been a laboratory that has sat down and said, we are going to study why alkaline water is good for your health. None. No scientific evidence. There's some random websites of people that are trying to commercialize alkaline water. This is the reality. For those people that have claimed that alkaline water alkalinizes your body, and now that your body's pH is at 8, 9, then that's why it's good for you. That is not correct. The pH of your blood is 7.4. Your pH in your blood never wants to be 9 or 10 or whatever crazy number they actually put out there. More importantly, you introduce alkaline water to your body, the blood buffer system takes care of it. It's going to pH it out. So you can drink as much pH 9 water you want. Your body is going to pH it or just take care of it through a buffer system, and your body wants to be at 7.4. Our stomach is super acidic also. So if you add something alkaline, of course, a neutralization reaction can also occur. So all these claims of, that, oh, I've heard it only once, and I just had to sit down and be like, okay, family, no, you're not gonna say this anymore. A student's like, oh, but the pH of my body is 9. I was like, what? Like, you will be dead, like legit dead. Look at the ranges. Like the pH in our body is so tight that I think at pH 7.3, I think, or 7.2 something, already it causes death. It's tightly controlled because the biochemistry in our blood, it has to control it. If not, the biochemicals or the biomolecules that we have are not going to be able to work. Enzymatic reactions are going to shut down. Anyways, so that's my opinion about alkaline water. If you take physiology, ask your physiology professor. Most professors also, also mention that, hey, if you drink something, have something with electrolytes, because electrolytes are much better for you. Yeah, go ahead. Some people like just the taste of it. Good, spend the money. You can spend the money, go ahead. But for nutritional purposes, alkaline water is not it. And at times, honestly, alkaline water is just overpriced electrolyte water. Now, the whole thing with purified water is interesting, because purified water, as long as it's not distilled water and deionized water, then that's different, okay? So we should stay away from deionized water. Deionized water is a water that doesn't have ions in it. It has no calcium, no sodium, no potassium, nothing. That is dangerous, because deionized water, again, we don't have scientific evidence, but I can say from my experience in the laboratory, deionized water, because water is one of those special molecules, is always searching for ions. And for example, for us in the laboratory, if we're using deionized water, we use it in reactions because we don't want the ions. But for example, if we have a water bath, we mix tap water and deionized water, because if not, deionized water actually corrodes metals because it's searching for those cations. Purified water, on the other hand, it's just purified through different column systems that is going to have some ion exchange. It will always have some trace elements trace elements, meaning some amount of cations there. Again, it is your choice. I'm not telling you one thing or the other. If you want to drink alkaline water, please do. If you want to drink purified water, do. I personally drink spring water just because I grew up on it. I'm from the northeast side of Puerto Rico, and over there, my parents, they have the water that reaches home is from the rainforest. So it's spring water, literally just they poke a hole in the ground and we have springs all over. Oh my God, drinking water from a hose. Yeah, I did that when I was a kid. I don't know whoever did that, especially on a hot day. And then my mom was like, well, there's water in the hose, and it's super hot water. Anyways, traumatized.
My immune system is perfect, by the way. Even drinking water from the hose.
As long as it's not hot, because I remember growing up on a hot day, like when you first turn it on and you're like, I'm so thirsty, and you're like, oh, it's so hot. And then you like have to let it, you know, run a little bit and then drink it. That was the life. See, it can burn your mouth. Exactly. That was my experience when you're a kid. And then we will all get grounded because drinking water from the hose turns into like us hosing each other with water. And then, of course, my mom and grandma were not having it. And that's part of being a kid. But finishing up the concepts for the blood buffer system. As I mentioned to you guys, the respiratory system can fluctuate the pH of our blood. So with that, the last thing that we're going to look is that the two conditions that we have illustrated here. The one on the left is called respiratory alkalosis, and the one on the right is called respiratory acidosis. As you can see here, in respiratory alkalosis, it can cause seizures, it can cause hyperventilation is one of the ways in which it can be caused. It can cause lethargy, confusion, lightheadedness, nausea, vomiting, and all that kind of stuff. Now, let's understand why is it that having respiratory alkalosis is a result of decreased CO2 levels. As you can see, the pH goes up. It can go up to 7.45, and it can be dangerous depending on how high your pH goes in your blood. So again, this is a buffer system that we have in our blood. And we are going to apply to this buffer system also the concept that we learned when it comes to the Chatelier principle. So when we have respiratory alkalosis, this is a system in which we have decreased amount of CO2. So we are removing reactant. If we go back to the table that we were working with, for this concept, let me just find it. When we are removing reactant, you can see that the shift of the direction of my chemical reaction is going to be towards the reactants. So if I go back into rationalizing this is going to move this way to alleviate that stress of losing CO2. As you can see here, if my direction is moving towards the reactants, because I'm trying to, again, equilibrate my reaction, what that means is that these two are combining to make carbonic acid to, again, alleviate the loss of CO2. Because we are combining H plus and HCO3, that means that we have less H plus in the system. And since we have less H plus, what that means is that we have an increase in pH values. Okay, so in the case of respiratory alkalosis, we have a decrease in CO2. The shift of the reaction is going to be towards the left, towards reactant. We're going to combine more of that H plus with that HCO3. So then biochemically, that carbonic acid turns into CO2 and water to alleviate that stress. And that results in an increase of pH in the blood. And that's what that is called, respiratory alkalosis. Let's move on to the other case, respiratory acidosis. When it comes to respiratory acidosis, okay, then as you can see here, this person is undergoing what is called hypoventilation, okay? So in hypoventilation basically means that you're trapping that CO2 inside of the body. You cannot release the CO2. That can cause drowsiness, muscle weakness, okay? Understand that even anesthesia can do this, overdosing, so on and so forth. Now, how does that change the pH of the body? As you can see, it's going to continue to go lower. Is going to be lower than 7.35. If we rationalize it based on the blood buffer system, this is how the blood buffer system is affected by this condition. In this case, we are increasing CO2. If we go back to the table that we were working with, we are adding reactant. When we're adding reactant, the shift in the direction of our chemical reaction is towards product. So that means that I add more CO2 in the system because, again, it's not being released. So it's just accumulating. So then that means that the shift is going to be towards products. So what's happening during respiratory acidosis is that CO2 is combining with water, and then that is forming carbonic acid. Then that carbonic acid is separating into ions. So in respiratory acidosis, we have more H plus in the system. And what that results, having more H plus, is a lower pH. Because remember that in the trend of pH, the higher concentration of H plus, that means a lower pH. The lower the concentration of H plus is going to be more basic, meaning a higher pH. So this is how respiration can actually create changes in the pH of our blood through the blood buffer system. Any questions about respiratory alkalosis or respiratory acidosis? Great. Since there are no questions, this is all the material that we need to know for exam 2.